Hello everyone. So welcome to the SATYAM live classes. I am SAGAR SHIROL from SB Darur Central School, Hargeri, and I am here to teach mathematics of 10th standard first chapter real numbers. So now in the previous standard 9th standard only we have studied that what are the real numbers. Yes, so real numbers means it is a collection of both rational and the irrational numbers. It is a collection of both rational and irrational numbers. Yes, so real numbers, collection of rational and the irrational numbers. And you have already studied that what is the decimal expansion of rational and the irrational numbers. Yes, so decimal expansion of rational number is either terminating or non-terminating recurring. Recurring means repeated. And what is the decimal expansion of irrational number? So that is non-terminating, non-recurring. Non-recurring. So for these examples you can write 2 by 3 minus 7 by 4 like this, and for the irrational number examples root 2, root 3 and so on. These are the examples, and this is the basic of the real numbers. And now here one thing you need to know, that for this academic year from this chapter real numbers, board has deleted the sum portion. So that is Euclid division lemma. So they have deleted the Euclid division lemma portion. But we are going to use the Euclid division lemma in the third exercise. So let's see just the statement of the what is Euclid division lemma. Okay, Euclid division lemma. So it says that for every two integers a and b, there exist two unique integers q and r such that a is equals to bq plus r, where 0 is less than or equals to r is less than b. So this is the Euclid division lemma. So it says that what, for every two integers a and b, so there exist two unique integers q and r such that a is equals to bq plus r, where 0 is less than or equals to r is less than b. Means, just take an example, 12 divided by 5. So if you divide this one, what you will get? You will get quotient as 2, because 5 2s are 10, and remainder as also 2. So we can write this as 12 is equals to, so that is b. B means divisor. So here divisor is 5 into quotient, that is 2, plus remainder is 2. So 12 we can write as 5 into 2 plus 2. So this is Euclid division lemma, and this is, the board has deleted this portion, but we are going to use this in the exercise 1.3, so I am explaining this one. So next After this, we will study that next section. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic. So before going to know this fundamental theorem of arithmetic, you need to know two things. That is, one thing is what is a composite number, and second one is what is a prime number. So what is a composite number? Composite number means a number which is divisible by itself and other numbers also. A number which is divisible by itself and other number also. For example, 4. So it is divisible by 2 also and 4 also. Divisible by itself also and other number also. So 12, it is divisible by 2, 3, 4, 6 and 12. So such type of numbers are called as the composite numbers. And next, what is a prime number? So prime number is a number which is divisible by itself only. A number which is divisible by itself only. For example, 2, 3 and next 5, 7, so on. So these are the example for the prime numbers, means a number which is divisible by itself only. 2 is divisible by 2 only by itself. 3 is divisible by 3 only, not any other numbers. So these are the prime numbers. So now we'll know that what is the statement of the fundamental theorem of arithmetic. So it says that every composite number. So just now we have studied that what is a composite number. Every composite number can be expressed as product of prime factors and this factorization is unique. So fundamental theorem of arithmetic, it says that every composite number can be expressed as product of prime factors and this factorization is unique. So this means what? Let us see an example. Take 100. So factorize this one. You know that factorization. So 2. So 2 pies are 0. And next 2 twos are 4. And next 2 pies are 10. And next 5 pies are 5 ones are. So 100 we can write as what? 2 into 2 into 5 into 5. So this is the factorization of 100. So let's see. So 100, it all contains the prime factors only. 2 is also prime and 5 is also prime. So every composite number can be expressed as product of prime factors. So it is 100 is a composite number and it can be expressed as a product of prime factors. And this factorization is unique. Unique means, so you can divide this by first number 5 also and you will get that what? 5 into 5 into 2 into 2. So but the multiplication you will get the same only, that is 2 into 3 is also 6, 3 into 2 is also 6, both are the same value. So the factorization is unique. So this is about what? Fundamental theorem of arithmetic. Okay students, let us take some examples. Factorize. factorize. Okay, just factorize this. So 250. So we can start from this one as 2. 2 ones are 2 twos are 4, and 1 remain 10, 2 pies are. And next 5 twos are 10, 2 remain 25, 5 pies are. And next 5 pies are 5 ones are. So factorization of 250 we can write as what? 2 into 5 into 5 into 5, or you can write this as 2 into 5 cube. So second one is what? 722. So just factorize this one. Okay, 2 threes are, 2 sixes are, and 2 ones are. So 361. So it is a prime number. So let us take this one as 361 are. So 722 we can write as what? 2 into 361. So this is the factorization of the 250 and the 722. Okay students, next we will study that how to find the LCM and HCF of any two numbers. Finding LCM and HCF of any two given numbers. Okay, for finding the LCM and HCF of any two numbers, we need to follow this. That is, for finding HCF, so it is what? So product of smallest power of each prime factor. So for finding the LCM HCF of any two numbers, we need to follow this. That is, product of smallest power of each prime factor. So okay, let us see. So now what is the, how to find the LCM and what do we need to proceed? So let us say that LCM is equals to product of greatest power of each prime factor. Okay, sorry students, here I made a mistake. That is, HCF is product of smallest power of each common prime factor, and here it is LCM. In the LCM, product of greatest power of each prime factor. So that is, let us see how to find the LCM and HCF of any two numbers. So let us take an example. Okay, take an example. Find the LCM and HCF of 225 and 520. Okay, for this, so we need to factorize these two numbers first. So first factorize those two. So 225. Okay, we factorize these two. We can use that 5. So 5 4s are 20, 2 remained, 5 5s are, and next 5 9s are 3 3s are 3 1s are. So 225 we can write as what? 5 square into 3 square. And 520. So just factorize this. 2 2 2s are 4, 1 remain 12, 2 6s are. And next 2 1s are 2 3s are. And next 2 6s are 12, 1 remain 10, 2 5s are 10. And next 5s are. Okay, 5 1s are 5 3s are. And next, so 13 1s are. So here 520 we can write as what? 2 3 are there, so we can write this as 2 cube into 5 into 13. So now how to find the, after factorizing this, how to find the HCF and LCM? So just see that what its HCF says, product of smallest power of each common prime factor. So in that let's see that HCF. First see that which are the common primes. So in this, so here there is, so nothing common is there. So what we can write here now? Sorry, so 5 it is there. 5. So in that smallest power which one is there? 1. So HCF is 5. And next LCM, what it says? Product of greatest power of each prime factor. So which all are their prime factors? So you need to take that multiplication. So if there is a common, then in that you need to take highest power. So here it is 5 and 5 common is there. In that highest one, which one is there? 5 square. So you need to take 5 square and take remaining prime factors also, that is 3 square into, here what is remained again? 2 cube into what remained? 13. So just do that multiplication. 5 square is 25 into 3 square is 9 to 2 cube is 8 into 13. So if you multiply this one, you will get 1,17,000. So this is the LCM. Okay students, let's see once again how to find the LCM of any two numbers. So just take that, find the LCM of and HCF of 225 and the 520. So just factorize these two first, and you know that how to factorize it. So here for HCF, what is the condition? Product of smallest power of each common prime factor. So see that which are the common are there. So just see those first. In that take smallest one. Here 5 common is there. In that smallest power is 1. So the HCF is 1. And next LCM, it says that product of greatest power of each prime factor, means every prime factors you need to take. So here what is there? So if there is a common, in that you need to take highest power. So 5 common is there. In that highest one is what? 2. So 5 square. And next 3 square. And next what is there here? 2 cube. And next remaining is 13. 5 square is 25, 3 square is 9, 2 cube is 8 and 13. So if you multiply this, you will get how much? 1,17,000. And students, dear students, here see one thing, that is just multiply LCM and HCF and the given two numbers. Just see what you will get. Sorry, this multiplication will give how much, means 23,400. Sorry students, dear students, let's make it a correction. I'll just multiply now LCM into HCF. LCM how much is there? 23,400 400 into HCF, how much is there? 5. So just multiply these two, just see how much you will get, means that now 1,17,000, and multiply the given two numbers. So 225 into 520, so which is equals to, so if you multiply these two also, you will get how much, means 1,17,000. So means LCM into HCF, it will give that product of two given numbers. So by this we can find a relation, that is LCM into HCF is equals to product of two given numbers. Okay, by this we can find a relation, that is LCM into HCF is equals to product of two given numbers. This is a relationship between the LCM and HCF and the two given numbers. Okay, dear students, let us take an example from the exercise 1.2. So in that, find the LCM and HCF of, so 26 and 91, and verify the relation, that is LCM into HCF is equals to product of given numbers. Okay students, so now solve this. So factorize first those two numbers, 26. So we can write this as 2 1s are 2 3s are 13 1s are, and next 91. So here we can write this as what? So we can write this as 7. So 7 1s are, again how much remained? 2, 21, 7 3s are, so now 13 1s are. So 26 we can write as what? 2 into 13, and here 91 we can write as 7 into 13. So here now HCF, which is equals to what it says? Product of smallest power of each common prime factor. See which is their common prime factor, that is 13. So 13 is the what? HCF. And LCM, which is equals to, so it says what? Product of greatest power of each prime factor. So what are all their prime factors? Multiply those. So 2 into 13 into 7. So if you multiply this, so you will get how much, means 182. So now verify the relation. So that what we can write here now? Verify that LCM into HCF, which is equals to, so now see, so LCM how much is there? 13 into, so LCM HCF is 13 and into LCM is 182. Multiply these two, so you will get how much, means 2366. So now multiply the given two numbers, that is product of given numbers, which is equals to, that is 26 into 91. So if you multiply these two also, you will get how much, means 2366. So by this we can say that it's verified the relationship, that is LCM into HCF is equals to product of two given numbers. Okay, dear students, so just see once again. So that is, find the LCM and HCF of 26 and 91 and verify the relationship LCM into HCF equals to product of given numbers. So just first factorize this 26 and 91. What you will get? 26 you will get 2 into 13 and 91 you will get 7 into 13. So HCF means what? Product of smallest power of each common prime factor. So common it is 13, so HCF is 13. And LCM is what? Product of greatest power of each prime factor. So what is there now? 2, 2, 13, and here remaining is 7. So if you multiply, you will get how much? 182. So now multiply and verify the relation. So LCM into HCF. So 13 into 182. So you will get how much? 2366. And product of given numbers. So 26 and 91. So if you multiply these two, you will get again the same value, that is 2366. So it's verify the relationship. And you can try the remaining examples of the exams exercise 1.2 second main question in home. So now let us see some more examples. So let us take an example that check whether 4n can end with the digit 0 for any natural number n. Okay students, let's see the example. Check whether 4n can end with the digit 0 for any natural number n. Okay, let us see. Is it end with digit 0 or not? So if any number ends with digit 0, then it should divisible by 10 or both 2 and 5. So let's see that if any number ends with digit 0, then it should divisible by 10 or both 2 and 5. So it of course, so any number ends with 0, for example 520, so it is ends with 0 means it is divisible by 10. And next take 750, so it ends with 0, so it is divisible by the 10. If it is divisible by 10 means it should be divisible by 2 and 5, because 10 is a product of factors of 2 and 5, so it should divisible by 2 and 5. So now, so it means what? It means the given number should contain and 5 as its prime factors. So it means what? If any number ends with digit 0, then it should divisible by 10 or both 2 and 5. It means what? The given number should contain 2 and 5 as its prime factors. But let's see here now. But 4 raised to n, which is equals to what? 4 we can write as 2 into 2 whole raised to n, contain only 2 as its prime factor. So just see, 4 we can write as 2 into 2. So prime factorization of 4 contain only 2. Here 5 it is not there. So hence we can conclude that what? So 4 raised to n cannot end with digit 0 for any natural number n. Hence 4 raised to n cannot end with digit 0 for any natural number n. Okay students, let's see once again. What is this? Check whether 4 raised to n can end with digit 0 for any natural number n. This is the question. So let's check whether it is ends with 0 or not. So now if any number ends with digit 0, then it should divisible by 10 or both 2 and 5. So it is, of course, if any number ends with 0, then it should divisible by 10. So now it means the given number should contain 2 and 5 as its prime factors. If any number ends with digit 0, then it should contain what? Both 2 and 5 as its prime factors. But 4 we can write as 2 into 2 whole raised to n, contain what? Only 2 as its prime factor. So here in this factorization only 2 it is prime factor is there. So hence we can conclude that what? 4 raised to n cannot end with digit 0 for any natural number n. So this is the solution of this problem. Okay dear students, so similarly another one example is there in the exercise 1.2 question number 5. So check whether 6 raised to n. So 6 raised to n can end with digit 0 for any natural number n. So you can try it as in home. Okay, let us see the next example. Given that HCF is equals to, or HCF of two numbers they are given, that is 306, 657, which is equals to how much? Means 9. Then find LCM of 306 and 657. So here they are given HCF already 9. We need to find the LCM. So for this, so by using the relationship we can find this one. That is, relationship is what? LCM into HCF is equals to product of given numbers. Yes. So here we need to find LCM into HCF. They are given how much it is? 9, which is equals to product of given numbers. Given numbers are which are there? 306 into 657. So 306 into 657. So here we need what? LCM. So LCM is equals to 306 into 657. So if you take this to the RHS, that will become division. So 9 ones are, so here it is 9 3s are So 27, how much remained? 3, 36, 9 4s are 36. So 34 into 657. If you multiply this, you will get how much means 22,338. So here it is what now? Answer is 22,338. So this type of examples are important for 1 mark in the MCQ, or they solve this as like they may ask. So dear students, next see the next example. Explain why 7 into 11 into 13 plus 13 is a composite number. So explain why 7 into 11 into 13 plus 13 is a composite number. So I already said that what is a composite number? Composite number means a number which is divisible by itself also and other number also, or you may say that a composite number which can be expressed as its product of prime factors. So if a given number can be expressed as product of its prime factors, so then it should be a composite number. Let us see why this is a composite number. 7 into 11 into 13 plus 13. So here this is the one part and this is the other part. So in these two, what is the common? 13. So let's take that one as a common. 13 into, so what is now here? 7 into 11 into, so we have taken that 13 as a common. Here remained is 1 plus 1. So which is equals to 13, 7 11s are 77 plus, what is there here? 1. So 13 into 77 plus 1, 78. So here the given number can be expressed as product of two numbers, so hence it is a composite number. It is a product of two numbers, hence it is a composite number. Means what? So here the given number can be expressed as two product of two numbers, so it is a composite number. So hence the given number is a composite number. Okay dear students, so see the next section, that is revisiting irrational numbers. Okay, revisiting irrational numbers. So you already know that what is an irrational number. Irrational number means a number which cannot be expressed as a P by Q form. So such numbers are said to be the irrational numbers. So in that, so let us see some examples on that. Before going to that, let us see a statement of one theorem. That it says that let P be a prime number let P be a prime number if P divides A square, then P divides A also. Means, what is the meaning of this theorem? Means, if let P be a prime number. So for example, take that one as 2 is a prime number. So if P divides A square, means 2 divides 2 square. So of course 2 divides the 2 square. 2 square means 4. So 2 automatically divides the 4. So then P also divides the A. So 2 divides 2 square means 2 divides the 2 also. So it is the theorem. This is the theorem. We are going to use this in solving the next problems. That is, P be a prime number. If P divides A square, then P also divides what? A. So this theorem we are going to use in the next solving examples. So just see that statement, not proof. This is proof is not there for you. So just this is the statement. Prove that root 2 is an irrational. Okay, already you know that root 2 is an irrational in the 9th standard. Yes. So now here we will prove that one root 2 is an irrational. And we need to prove this by contradictory method. Means by assuming that this is a rational number, we need to show that it is not a rational, it is an irrational. Let us see how to prove this one as a irrational. So let us assume that root 2 is a rational number. Okay, just assume that it is a rational number. So then there exists two integers A and B such that A by B is equals to root 2. Why this one? Because we have assumed that root 2 is a rational. So you know that every rational number can be expressed as A by B form or P by Q form, where A and B are co-primes. So here comes again one new word, that is co-prime. Co-prime means both the numbers which are divisible by only 1, means 2 and 3. So both the numbers are divisible by 1 only, or 3 and 5, 7 and 11. So such type of numbers are said to be the what? Co-primes. Means both the numbers are divisible by 1 only, not any other number. Such numbers are said to be co-primes. So here A and B also what? Co-primes. So now here, okay, let us take B to the RHS. What it will become? A is equals to root 2B. Square on both sides now. Square on both sides. So square that one, A square, and this will become 2 root B whole square. So here A square is equals to, so you need to square both. Square root of 2 whole square, you will get what? 2, and this one is B square. So this implies now what we can write here? 2 divides what? A square. So you may ask, why how 2 divides a square. So here, since 2 divides 2b square, because 2b square is a multiple of 2 is there, so hence 2b square divisible by the 2, and here equality is there. So if 2b square is divisible by 2 means then a square must and should be divisible by 2. So 2 divides a square. This implies 2 divides a. So as you already know that theorem, if p divides a square, then p also divides what? A. So by that 2 divides a. Let us take this as equation 1. So now apply Euclid division lemma. Euclid division lemma for 2 and a. So already we have studied that Euclid division lemma. So now apply Euclid division lemma for 2 and a. So what we can write this one as a is equals to 2q plus r. Here 2 is the divisor. So what is the Euclid division lemma? That a is equals to bq plus r. So here b is equals to 2 is there. So a is equals to 2q plus r. So this implies a is equals to 2q because r is equals to 0. Why r is equals to 0? So 2 exactly divides the a. If any number exactly divides the another number, then remainder should be 0. So hence a is equals to 2q. So now again same, square on both sides. Okay, square on both sides. So just square on both sides, what you will get that? A square is equals to 2q whole square. So this implies 2 square, a square is equals to 2 square is 4, and next q square. So here now a square, what is there here? A square value is 2b square. I will take that one. 2b square is equals to 4q square. So you can write in the bracket, since a square is equals to 2b square. So now take 2 to the RHS, it will divides 2 1s are 2 2s are. So what we can write now? That one, b square is equals to 2q square. So again it is same now, what? 2 divides b square. Why? So here 2q square is multiple of 2 is there, 2 divides 2q square. So equality is there, hence 2 also divides b square. So this implies now 2 also divides what? B. Let us take this as equation 2. So now let's see that from the equation 1 and 2, what we can conclude that 2 divides both a and b. But what we have assumed that a and b are the co-primes. So means co-prime means what? Both should be divisible by 1 only. But here what is C? From equation 1 and 2, both are divisible by 2. Means we can conclude that a and b are the not co-primes. So this opposition occurred because of our wrong assumption, that is root 2 is a rational number. So you get the opposition or you get the contradiction. Here both a and b are divisible by 2. This has occurred because of our wrong assumption, that is root 2 is a rational numbers. Hence we can conclude that so root 2 is an irrational number. This is the contradictory method of the proving this example. So here what? From equation 1 and 2 we can observe that 2 divides both a and b. This is opposition to the fact that A and B are co-primes. So just see here what from 1 and 2 we can observe that 2 divides both A and B. This is opposition to the fact that A and B are co-primes. So hence, this opposition has occurred because of, just see, I will write here, because of our wrong assumption. This opposition has occurred because of our wrong assumption that root 2 is a rational. Why this opposition has occurred? Because of our wrong assumption, that is root 2 is a rational. Hence, we can conclude that root 2 is an irrational number. Hence, root 2 is an irrational. Okay, dear students, just see once again how we can prove this one, root 2 as a irrational. So we need to prove this by contradictory method, means by assumption method. First, let us assume that root 2 is a what? Rational number. Then there exist two integers A and B such that A by B is equals to root 2. So every rational number can be expressed as A by B or P by Q form. So A by B equals to root 2, where A and B are co-primes. Co-prime means numbers which are divisible by 1 only, not any other numbers. So here now take B to the RHS. A is equals to root 2B. So now square on both sides. So A square equals to what you will get? 2B square. So now 2 divides A square. How it means? 2 is, B square is a multiple of 2 is there. Hence 2 divides 2B square. So it is equality. So 2B divides 2B square means then 2 divides A square also. So 2 divides A square means 2 divides A also, by the theorem that if P divides A square then P divides A also. So let's take this as equation 1. So now apply Euclid division lemma for 2 and A. Here 2 is the divisor and here A is the dividend. So now by Euclid division lemma what we can write? A is equals to 2Q plus R. So here it will become A is equals to 2Q because remainder is 0. Because if any number divides the other number exactly, then remainder should be what? 0. So A is equals to 2Q. Now again square on both sides. What you will get here now? A square equals to 2Q whole square. A square equals to 4Q square. So now just take 2 to the RHS, that will become division, just divide that. You will get that B square equals to 2Q square. So now here this will become what? 2 divides B square, as again 2Q square is a multiple of 2 is there, hence 2 divides 2Q square. Here it is equality means 2 also divides the B square. So therefore 2 divides B also. Let us take this as equation 2. So now just see that from equation 1 and 2 we can observe that 2 divides both A and B. So this is opposition to A and this is opposition to the A and B, that A and B are co-primes. Here it is, just right there only, A and B are co-primes. This is both divides A and B. This is opposition to the fact that A and B are co-primes. This opposition has occurred. Why this opposition has occurred? Because of our wrong assumption that root 2 is a rational. So hence root 2 is an irrational number. Okay dear students, so we will complete this session. Again remaining we will continue in the next section.
ವೀಕ್ಷಕರೇ, ನಮ್ಮ ಸತ್ಯಂ ವಾಹಿನಿಯ ಪ್ರತಿದಿನದ ಅಪ್ಡೇಟ್ ಮಾಹಿತಿಯನ್ನ ತಿಳಿದುಕೊಳ್ಳಲು ಸತ್ಯಂ ಟಿವಿ ಕನ್ನಡ ಯೂಟ್ಯೂಬ್ ಚಾನೆಲ್ಗೆ ಸಬ್ಸ್ಕ್ರೈಬ್ ಆಗಿ ಹಾಗೂ ಬೆಲ್ ಐಕಾನ್ ಅನ್ನು ಕ್ಲಿಕ್ ಮಾಡಿ.